Good day, everybody, and today we'll be covering a particular presentation on generative adversarial nets, or GANs, and my name is Joseph Atoba Akande, and I'll be taking you through this lecture today. So let's get into it. So the overview, we're going to start with the introduction. We're going to look at the structure of GANs, adversarial networks, and their algorithm, theoretical results of this paper, the experimental results, the advantages and disadvantages of using this kind of model to train a neural network, and then this is project's impact and conclusion. So, this paper was a very important paper in the history of neural networks and machine learning in general, as it introduced a new way of training neural networks and generating data, right? So at this point in history, this is 2014, we already knew how to build really good classifiers. But then when it comes to generating new data, the structures we had, the models we had were very primitive. They were not good at their job. So this paper kind of sought to use the power of the very good classifiers we have and use those in training a generator, right? So uh, GANs are generative models which create new data instances that resemble the training data, right? So a GAN could create the image of a person that doesn't exist in real life, right? This person does not exist, but a GAN takes the training data and creates new instances of data based on what it has been trained on, right? So GANs achieve this level of realism by pairing a generator, which we would have as G, and produce an output with a discriminator, which we'll be talking about as D, right? So the generator's work is to try and create fake data to fool the discriminator, and the discriminator tries to keep itself from being fooled. So you can liken this to a game of a cop and robber, or in this case, cop and counterfeiter, right? So you have a counterfeiter creating fake money and trying to use that money, while the discriminator is trying to figure out which notes are counterfeit and which ones are original, right? So you can liken it to that, and we'll do that in the next slide actually. So you have the generator starting off really bad. It's trying to create fake money, doesn't know how to do it. All it says is the 10 and maybe a face, and it creates that data, sends it to the discriminator, who recognizes it as obviously fake, right? It knows that that node is fake, so it tells the generator do better. That's obviously fake, and the generator takes this feedback through back propagation, and it starts getting better at its work. The discriminator still recognizes it as fake, and it passes on that information to the generator, but it's getting better. And eventually, through many iterations, we start to get a result where the generator is pretty good at um, creating fake data, and the discriminator has no idea anymore. It doesn't know which data is being created by the generator and which one is coming from the actual training. So if we look at the structure of a GAN right here, um, we can see that the discriminator is simply a classifier, right? It's taking samples from the real image set, those go into the discriminator, and then the generator is creating its own samples that are similar to the image set that we have. And by images, we're just using images here as they're way easier to present and visualize. This can be any form of data. It could be audio files and so on and so forth. So it also passes off its sample as real into the discriminator. Now the discriminator has to figure out if this is real or not, and then it creates the loss functions, which then go back through back propagation, and then the process repeats itself. All right. So that's the structure of the GAN, and the generator basically just has to create fake data and incorporate that and get that feedback from the discriminator, and then get better at its job. So that's how the GAN structure works. There is no direct communication between the discriminator and the generator. All that it's getting back is the loss functions, right? So Moving on. So we just talked about the loss function, right? So for adversarial nets, the discriminator and the generator, they try and play a min-max game defined by the value function v of g of d, right? And this value function right here, is defined as the log probability of the discriminator. The log probability of the data, the actual data, the real data, and the log function of the fake data, which is log 1 minus d of the generated samples, right? And if we look at a closer look at this equation, this is basically the log probability of it being real data, right? This is the probability of the data sample being real, and this is the probability of it being fake. So if we take a look at this, we have a prior function for the noise distribution, which basically we input noise into the generator basically, because a neural network like this is non-stochastic, and we need a way to generate random samples, so it's not just a one-to-one representation of the given data. And that noise function, that input noise goes into the generator, g of z, and that produces it produces an output, right? It produces the fake data that goes into the discriminator, right? So the discriminator, max v, is trying to maximize the probability of it being real data. It's trying to get this up, the probability of it being real data, and trying to minimize the fake probability. So the discriminator is trying to maximize this, but it's trying to minimize this, right? While the generator, there's a different color for this. The generator is trying to minimize the entire thing, because this entire thing is the probability of it being real data, right? So it's trying to minimize the entire objective. It's trying to minimize the best possible, because the combination of this is going to give you the best possible discriminator, and the generator is trying to minimize the best possible discriminator, if that makes sense. So that's how the loss function works. But then when you go into practice, you realize if we're minimizing this right here, in practice, it doesn't work, because in the earlier iterations, when the data is obviously fake, this is going to be max, and it will just kill the process way too fast. So in the earlier stages, instead of minimizing this loss function, we actually train G to maximize the probability of it being fake. We're trying to maximize log d g of z. So the fixed point of these equations are the same. It's just going to give these two equations, their fixed point is the same. We're getting the same result. We're just a different method to the same madness, I guess. Moving on. Go on to the next slide. Okay, so this is how GANs train, right? We have four recognizable phases, if you may say. So we have the Z space, which is projecting onto X. So if you look at the first diagram here, we have the Z space projecting onto X, where the space between X and Z and X is G, which is the generator. So we see the data samples, they're being projected onto random points here. So this blue line is the discriminator. Excuse me. The blue dots are the discriminator. The green line, this one right here, is the generator, and the black dots are data, right? So we see the Z space is projecting the samples onto X, and the discriminator is all over the place, right? It's all over the place. You just see it all over the place. and we see the generator is also just to understand why the data is fixed, right? So here we maximize D, right? We maximize D, and then we get this function right here. We get this function right here. And what you have to note is this function goes in this direction, right? It's going in this direction. It's basically the probability between the fake data and the real data, where this black one is the real data and the green one is the black data. But because the real data never sees the fake data never sees the real data, it can only move along this curve, what the discriminator gives it, right? So this green line starts to shift in this direction. 1 second, it starts to shift in that direction. And what that gives us is minimizing, by this, we're going to be minimizing the objective. We're going to be optimizing the generator by minimizing G. So the data starts to shift. As you see this green line, it starts to shift in this direction because that's the direction of the discriminator curve. So we see the green line starts to shift in this direction until it matches the curve through many iterations, right? We have this dot means many iterations, and then we can see the samples are being projected directly, right? So, and then you see the discriminator ends up confused. It ends up as half or 50%. So at this point, the discriminator does not know whether the green line is fake or real anymore. It just goes flat, which is half, which means there's a 50% chance the probability of the data is the generated data, the actual data is equals to the probability of G, which is the generated data. So it doesn't know anymore and it goes flat. So that's how GANs train, and this is the optimum function. And yeah, so moving on. So for the theoretical results, we have the algorithm, which basically just says for this amount of steps, you sample a mini batch from the noise samples. That's the input. For the to get random generated samples, and then you take a sample of the mini batch of M, for example, blah blah blah, and that is for the actual data. So for every step, you update the discriminator by by taking the stochastic gradient up, and then you end the iteration by sampling the mini batch of the same thing for the generated samples. So this was for the training samples, this would be for the generated samples, and then we take this out because we don't need it anymore, and then that's when the iteration ends. So we do that for one step, right? That's for one step, and that's what the authors did, and that's what I believe is still being used till today. So yeah, moving on. And then the main theory which they proposed in this paper was that the global optimum of this of our loss function of that algorithm would be when P of G is equals to the P of data, which is the probability of the generated data, is equals to the probability of the actual data, right? And the global minimum, they were also able to calculate that even way early, even in the first paper. They defined the global minimum to be minus log 4, because when P of G is equals to P of data, remember, then the G of X, which we talked about, would be half, right? Because the generator has no idea anymore. The curve goes straight. And when that's half, we have log 1 over 2. And if this is log 1 over 2, then this is also log 1 over 2. And when you add it together, we get minus log 4. So they were able to define the global minimum. And so yeah, that was one of them. That's the main theory that this paper proposed, and they were able to prove it that way. So for the experimental results, so they took their algorithm and then they trained it on 3 different data sets, right? The eminence data sets, which we all know and love. So that's a data set of numbers, and the rightmost column right here is the nearest training example to the generated data. So these are the generated data. This is G, and this is actual data. The yellow boxes is actual data. So looking at the MNest example, we can see that the algorithm is very well able to generate random numbers that the that's not in the actual training data without memorizing the training data. But then we can also see in some cases the algorithm somehow kind of um what's it called, remembers the training data, because if we look at samples like this, we can see very close similarities. That also works. You can see that here. You can kind of see that here. But then if you look at the generated samples for 2014, these are exceptional. So the generator is this is proof that the generator is actually working. You can see you can see features, you can see the eyes, the mouth, the nose. In some places it is blurry, and we can, but for its time we can see that these are well generated samples, and there's a future for GANs here. So um so this was from the Toronto face dataset, I think it's called. And for this, for all three of these were using fully connected models, the CNN layers. Um, was it the CNN layers and the layers? Sorry. In these, for these three, they were fully connected models. For these, they used a convolutional discriminator and a deconvolutional generator, and this would eventually kind of lead into the newer ways which we generate data now. But yeah, so even back then, they were able to, estimate that this could be a solution to other problems. So if you look at the actual numbers for these results, we still don't have really uh, good ways to measure um, generated data, how accurate they are. But with the ways we have, we can see for adversarial nets, they had the highest probability that the generated data would be recognized as fake data. And these were done in random draws. These were not cherry picked, or you look at the ones that were really close to training data. This is all random. And this was on the MNIST dataset. It performed the best compared to models at the time. And when they used the TFD, the Toronto face dataset, it was the second best, really close to the stacked CAE, as that could recognize faces better. But these were the log likelihood estimates that the fake data would pass as um, actual data. So yeah, those were their experimental results and the advantages of this paper. This paper was able to fully get rid of Markov chains, and there was no only backpropagation was used to obtain the gradients. Only backpropagation was used. They didn't need any extra computational power. There was no inference needed during learning, and there were a wide variety of functions that could be incorporated into the model because it's just a log function. So, and for the disadvantages, there's no explicit representation of P of G of X. So the generated data during training is not fully represented. It's only sampled in back through back propagation. And then the discriminator must be synchronized well with the generator, unless, because if you don't update the discriminator often and the generator just keeps getting better and better and there's no penalty, then it gives this problem, right? Where the discriminator is just starts to lose steps and starts to lose efficiency. So yeah. So this project's impact, right? This paper introduced a groundbreaking framework for estimating generative models using a different approach, and this model basically opened the doors to GANs as we know them today. I believe this paper was way ahead of its time. So this paper, just a beast of a paper, really. It was 8 pages long. I say it defines how we look at image generation and AI today. So yeah, this paper was really significant, and it established this new generation of generating realistic fake synthetic data. And for the conclusion, we conclude that we are providing a good mechanism for training generative models. The paper's key findings: it leverages a two-player min-max game to generate realistic data. It's able to generate the visual data across different data sets. And despite challenges such as mode collapse, this paper was still able to outperform its peers at the time. So yeah, that's the conclusion for the paper. And thank you very much for listening. I hope you did have a blast. This paper was really, really um, eye-opening. I enjoyed going through the paper and researching on it and seeing and watching and Goodfellow actually, present the paper in conferences. This was really inspiring. So thank you for that. And yeah, so thank you and do have a great day.